Okay, so hi there everyone. We're now on our next video in number theory, and here we're going to continue with our discussions in the classical milestones in number theory. We're done with Wilson's theorem. We're now going to venture with Fermat's little theorem. So we all know the mathematician, if you don't know him yet. So the name of this mathematician is Fermat. Okay. In fact, the full name is Pierre de Fermat. Okay, Pierre de Fermat. So this is one of his theorems, little theorem. We call this Fermat's theorem to distinguish it with Fermat's last theorem, which is, of course, one of the most famous theorems or conjectures that that um that we know, which was solved by Andrew Wiles way back in 2004 or 1997. Forgot. But Fermat is not a mathematician. He is a lawyer, where he spend his free spare times in doing mathematics. So one of the famous works that he done is that commentary of the work of Diophantus in Arithmetica. So in that work of the Ephantus, what he did is to write some scribble notes at the side, and then put some comments there. And then after that, after his death, one maybe I think his son saw that work and then published it, and then saw that the work there is very fascinating. And then what we have now is Fermat's work, one of which again is the Fermat's little theorem. Um, let's have this. The Fermat theorem explains or tells us this. So it has the original theorem is theorem 4.9. The the extension of it is theorem 4.11. So let's start with theorem 4.9. Um, let P be a prime and A be any integer such that P does not divide A. So meaning A is not a multiple of P. Okay. So then we say that A raised to P minus 1 is congruent to 1 mod P. Okay, again, if P is a prime and A is any integer in which A is not a multiple of P, of that prime P, then A all raised to P minus 1 is congruent to 1 mod P. So another extension of this is if we're going to let P be a prime and then A be any positive integer, then A raised to P is congruent to A mod P. So this is a sleek theorem, which is also one of the most powerful theorems in number theory. Again, one of the classical milestones in number theory, and Fermat is one of them. Um, we can show that this is true in a little example that we can give. But let's go on to the applications. Okay, let's go to the applications of it. Where can we use this like this pure formula actually? So where can we use this specific formula? Okay, so for instance, let's have this application here. Okay, so one application of this is here. So for instance, we're asked to find um 3 raised to 31 mod 7. For example, we are asked to find 3 raised to 31 mod 7. So we know by Fermat's theorem that it states that if P is a prime and A is any number, okay, any integer, provided that P does not divide A, therefore we can say that A raised to P minus 1 is congruent to 1 mod P. It's congruent to 1 mod P. So we'll use that in our application here. So we are asked to find 3 raised to 31 mod 7. So since P, which is in the mod here, is a prime number, and we can see that A, which is 3, okay, is not a multiple of 7. So therefore we can apply Fermat's little theorem here. So therefore um we say by Fermat's little theorem. Little theorem. Since we have a p minus 1 is 6 is congruent to 1 mod 6. And if it is congruent to 1 mod 6, so it's 1. Okay, so we can disregard it since it's congruent to 1. So it's going to become 1 times 1 times 1. So going back here, applying that to the form, applying this here, thus, um, 3 raised to 31 actually is congruent to just or just equal to of saying just equal of saying 3 raised to 6 times 3 raised to 6 times 3 raised to 6. Okay, I think we need to add to it. Oops, I'm sorry. Let's write it down below. Sorry. So um 3 raised to 31, okay, is equal to 3 raised to 6 times 3 raised to 6 times 3 raised to 6. Of course, if we're going to do this manually, oh my goodness, that's not gonna be good. That's gonna be a very huge number. 3 raised to 6 times 3 raised to 6 times 3 raised to 1. Okay, because this is by the law of product of our exponents. So 3 plus 6 plus 6 plus 6 plus 6 plus 6, that's 5 of 5 sixes, that's 30 plus 1, that's 31. But we say that it should be 3, sorry. 3 3 raised to 6. My goodness. 3. So we say that 3 raised to 6 is equal to 1. So this becomes 1. Okay. Let me write that. Okay, so this becomes 1. This becomes 1. Since they are modulo 1, right? So this becomes 1, this becomes 1. Hence, therefore we can say that this is equal to 3 raised to 1, which is congruent to 3 mod 7. So hence, 3 raised to 31 is just actually congruent to 3 mod 7, which makes our solution very, very short and very, very um, easy to do. So that's by Fermat's little theorem. Another example. Another example. Oops. Okay, so let's have this. Find 2 raised to 35 mod 7. Okay, so by Fermat's little theorem, let's answer this. By Fermat's little theorem. It's too much. Little theorem. Since 7 again is the mod, so we say that 2 raised to 6 is congruent to 1 mod 7. 1 mod 7. So we have 2 raised to 35. So we say that 2 raised to 35 is equal to 2 raised to 6 times 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 this is 30, 2 raised to 5, right? Then we will cancel up the 2 raised to 6s because they're all congruent to 1. Therefore, this cancel up, cancel, this becomes 1, becomes 1, this becomes 1, this becomes 1, this becomes 1, and what we have left is 2 raised to 5. So 2 raised to 5 is just 2 raised to 5. Sorry, 2 raised to 5. Okay, and we say 2 raised to 5 is congruent to is equal to 32. And 32 is congruent to, in the mod 7 environment, we have 28, mod 4, the remainder is 4. So therefore the answer is mod 7. So therefore it's 4 mod 7. So therefore 2 raised to 35 is congruent to 4 mod 7. It's actually just 4. Okay, so that's the application of the Fermat's little theorem. Um, I'll be giving out the next of our theorems, that is Euler's theorem, in the last part of this chapter. So thank you very much for watching. I hope that you would like and subscribe. And yeah, thank you.